And I meant to be back on the book rather than here. So let's get me back to the book, the PDF of the book. All right, so I'm going to move you, up to the top. I think that goes better there. Yeah. All right. We have no questions from anything we've done so far. Let's pick up where we left off last time. I think I will scroll back up. I thought not, but okay, what we're dealing with now is homogeneous linear equations with constant coefficients. Okay, now homogeneous here means equaling 0 at the end, not the same thing we meant before. Okay, equals 0. Okay, now anytime you have constant coefficients, then your assumption is your solution for this will be in the form y is equal to e to the mx. Okay, then when you take a derivative of this, you get y prime is equal to m e to the mx. And as many derivatives as you take, then you just get more and more higher powers of the m here, right there, okay, and more, you know. So you get what they call an auxiliary equation, which actually, let me see if I can, yeah, right here. Okay, if this is your differential equation, a y double prime plus b y prime plus c y equals 0. Homogeneous because that's a 0, constant coefficients because these a, b, and c are just numbers. Again, the assumption is y is equal to e to the mx, and then for every one of the derivatives, see, y prime would be m e to the mx, y double prime m squared e to the mx. Every time you take a further derivative, you just introduce another term m. Well, once you do that and put all those in your equations here, every one of these, the y is equal to e to the mx, y prime has a e to the mx in it, y double prime has a e to the mx in it, every one of them does, so you can factor out the e to the mx. And that leaves you with this equation, a polynomial equation, no longer a differential equation, a polynomial equation in m. Now, remember, this is a homogeneous differential equation, so that's equal to 0. Well, e to the mx is never, ever, ever equal to 0. So you can factor that out. That means that your auxiliary equation, the polynomial equation, has to be equal to 0. And here's your manual. All right, good deal. All right. We've doubled the class size right then. And I think, Jermanuel, you heard about Wednesday, right? Well, I don't know if you're here yet. Okay, hopefully you did. All right, so this equation here, this polynomial equation in m, okay, is called the, oh, here comes the manual again. Okay, so he evidently didn't make it in the first time, or that time, or that time. So I keep admitting him, and he keeps not coming in. I don't know what it means to view. Let's view, okay. This happened before, didn't it? I can't remember if it was Jermanuel or somebody else. Kira, do you have a way to text him or message him or something to let him know I keep admitting him and he keeps popping back out again? It says he's joining, but then he doesn't, and then he goes back to the waiting room. Kira, do you have a way to contact him? Okay, this time it's taking longer for them to join, so maybe you'll make it. Nope, doesn't look like it. Let's see what message says. Okay, Kira, have you tried to get in touch with your manual? Well, this time it's taking longer for him to join. Let's see if he makes it this time. Well, he's still not in, but at least he's didn't kick him right back out. I hate to lose class time like this, but I want him to be able to come in if he is trying. Kira, have you been able to get in touch with him? Well, that time he left and didn't come back. Okay, well, we are recording. Hopefully you'll be able to come back in. Okay, so what we were talking about before, and let me see if he's still out there. Nope, there's only the two of us again. Okay. All right. So this is called the auxiliary equation. It's just a quadratic equation or a polynomial equation, okay? And if you can break it down into, get it down to quadratic form, then there are two roots to it. And we'll use the quadratic formula to get those: minus b plus or minus the square root of b squared minus 4ac over 2a. Okay? There will be three forms for the general equation, and we talked about this last time. The first of these are when m1 and m2 are both real and distinct equations. Okay, in other words, that's when your b squared minus 4ac is greater than 0. Okay, that means that radical does have solutions. Okay, real solutions, two real solutions. Other times, however, the m1 and m2 may be real and equal. That's when the discriminant of that equation, the thing under the square root, is exactly equal to 0. Then you only have one real solution, or it's a double solution. And then there are times when the b squared minus 4ac is less than 0. Under a radical, that means they're complex numbers, not real numbers, complex. They're always complex conjugates of each other when your coefficients are real. Okay? Now, we talked about the first two of these cases, the first one being when you have two distinct roots for that equation. Then you have c1 m e to the m1x, that's the first root, plus c2 e to the m2x, that's your second root. Okay? Because you have two real distinct answers for m1 and m2. That's all you need, because this is a quadratic, a second order differential equation. In the second case, however, when you have repeated real roots, when m1 is equal to m2, we have to obtain one exponential solution, y1 is equal to e to the m1x, but from the quadratic formula you find that that m1 is only minus b over 2a, since the discriminant, b squared minus 4ac, is 0. Okay? Well, then we use that root reducing formula that we did before, and it turns out giving us a x e to the m1x. That is a independent solution from e to the mx. Okay, e to the m1x is 1, x e to the m1x is second. That's going to be our general solution there. Now that's what we talked about last time. Now we're moving into case 3. Case 3, that's when m1 and m2 are both complex numbers. They happen to be complex conjugates of each other. Okay? Now here's what they turn out being. m1 is alpha plus I beta. m2 is alpha minus I beta. Complex conjugates of each other. Alpha and beta are both positive. They're both positive and real numbers. The I squared is minus 1, meaning I is the square root of minus 1. Now, you could write this solution, y is equal to c1, that's the arbitrary coefficient, e to the m1, which is alpha plus I beta x, plus c2 e to the alpha minus I beta x. Okay, that's the coefficient m1, there's the coefficient m2. However, in practice, we prefer to work with real functions instead of complex exponents. To do this, we use Euler's formula. Now this will take some time and effort to work your way through. I don't think we have class time to do it, but I'll try to give you the highlights of it. Okay, here is Euler's formula. E to the I theta is cosine theta plus I sine theta. Unbelievable, but a simple little formula like that developed by Leonhard Euler. Okay, I think he was a Swiss mathematician, one of the most prolific mathematicians of all time. Gauss was pretty prolific too, but he did a lot of work in physics as well as other types of fields. Euler, man, he was all over mathematics. He did physics work too, but boy, he was all over just tons of fields of mathematics. Okay, now this theta is a real number. Okay, we put the I there to make it complex here, e to the I theta, but theta itself is a real number. Cosine theta then would be a real number, but I sine theta would be sine theta would be real, but I sine theta would be complex. Okay, now if you were to take this e to the I beta x, okay, this second part here, e to the I beta x and e to the minus I beta x from here, okay, those can be written just like you saw here. This one here and that one there can be written as a real part and an imaginary part. That would be cosine beta x plus I sine beta x. This one would be cosine beta x times minus I sine beta x. And the reason for that is that sine is a odd function, cosine's an even function, so when you're dealing with that, change the sign, they change signs as well. When you change this sign here, the cosine stays the same, the sine does not. Now, this is what I was saying. Cosine of minus beta x is equal to cosine of beta x, because cosine is an even function. Sine of minus beta x is equal to minus sine of beta x, because sign as an odd function. Note that the first adding and subtracting the two equations here together, first add them, and you'll get e to the I beta x is equal to cosine beta x plus I sine beta x. Add to that to e to the minus I beta x, which would be cosine I beta x minus I sine beta x. Add those two together, these two terms will disappear because they add to 0. So then you get the sum of this one plus that one is equal to 2 beta x, 2 times the cosine of beta x. Okay? Now, if you subtract the two equations, in other words, subtract this one from that one, you get e to the I beta x minus e to the minus I beta x. Then their cosines would divide away or subtract away, and you get 2 I sine beta x. Okay? Now, so that's what the first one gives you, 2 cosine beta x. The second one gives you 2I sine beta x. Now, since the y from up here is equal to the sum of those two entities, okay, that's the solution of 2 of that original differential equation. For any choice of constants C1 and C2, you can have that the that C1 equals C2 is equal to 1, or C1 is equal to 1 and C2 is equal to minus 1. Now, because it could be true for any value C if you choose those two C's. Now, in the first one, where the C1 and C2 are both equal, then you're adding these things together, and that's when you eliminate the I term, you know, the I sine beta x. That goes to 0. When you do the second one, C1 is 1 and C2 is minus 1, then you wind up with 2 times I e to the alpha x sine beta x. Okay? Now, before we move along, let's just note this footnote here. Formal derivation of Euler's formula can be obtained from the Maclaurin series, and by the way, both of those names are potential paper topics, both Euler and Maclaurin, and substituting, I can't read because that block is in the way. Hold on just a moment. Okay, Maclaurin series there. Either of those could be paper topic by substituting x equal I theta. I just didn't get it set in time. Now, the plausibility thus established, blah blah, from what they were saying here, there's a definition of e to I theta. We're just going to leave it alone. All right, now, hence the corollary A of theorem 4.1.2, okay, and the last two results, okay, now I didn't go back and show you that one, but let me just point you back to it. 4.1.2 is quite a few pages back. It's the Wronskian, okay? The last two results show that e to the alpha x cosine beta x and e to the alpha x sine beta x are real solutions for the original differential equation 2 that we had. Moreover, those solutions form a fundamental set from negative infinity to positive infinity. Consequently, the general solution is, this is the bottom line, okay? When you have your M1 and M2 being complex numbers, okay, e to the alpha x, e to the I beta x, okay, when you have that, then you can rewrite, using Euler's formula, this to be a real number, c1 e to the alpha x, cosine beta x, plus some c2 e to the alpha x, another real value, sine beta x, okay? So you can pull out the e to the I beta x, that's in both of those, and then have c1 cosine beta x plus c2 sine beta x, okay? Now, I know that was a lot of blah, 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 and it looked like to me they were sort of playing a shell game, but it does work. It just takes a lot of steps to fill in all the steps they skipped. So let's see practical example here, second order differential equations. Let's go to our whiteboard and see what we get here. I'm going to move Kara back down. I don't know why it's just Kara now, but it used to be all of us there, but now it's only Kara. But I'll move her sort of to the side here. And if I could get my pen and the pad down here, we can do it. Okay, here's example 1. Solve the following differential equations. Okay, if I could get my pen to show up. There it is. Now I thought I had moved all this around. Evidently I forgot this part. Hold on a moment. I did this when Kara and I were the only two here. I thought I did, but evidently I didn't do enough. Okay. Solve the following differential equations. Here's the first one. 2y double prime minus 5y prime plus 3 or minus 3y is equal to 0. Okay. Now, this is obviously a second degree linear differential equation with constant coefficients. Okay. Now I'm going to start off doing this most times. After a while I'm going to quit. When you have the constant coefficients there, and they don't have to be integers like you see here, any constant coefficients, they just can't have x's or y's in them, any constant coefficient. We're going to be real too. We're not going to have any complex coefficients. Okay, here is your assumption. A solution is y is equal to e to the mx. Okay, now again, I'm not going to do this every time, but I'm going to do it to the beginning. Okay, then y prime, goodness gracious, this thing is so aggravating, y prime is equal to m e to the mx, and y double prime is equal to, I can't write, equal to e, goodness gracious, this thing is so aggravating. Okay, I'm going to try to erase some of this because it's so messy. Okay, is equal to m squared e to the mx. Okay, so when you plug all these things in here, you get 2m squared e to the mx minus 5m e to the mx minus 3 e to the mx. Can't get the pen to write well. And that's equal to 0. Well, obviously every term here has a common factor of e to the mx in it. Now we don't know what m is, but that's okay. And what's left when you factor that out is 2m squared minus 5m minus 3 equals 0. Okay? Now, these are two factors equaling 0. This one cannot ever be 0. E to the mx is always greater than 0. Always. So divide it away. And that's why I'm going to quit writing it down after this one. It's always going to divide away. That leaves us a polynomial equations here. And let's see first if we can factor it. Well, that would be 2m times m. Okay. Now, this last sign is negative. That means these two have to be different. So I'm going to put this one as a plus here and a minus there. Okay? Now, let's try putting the 6 here. Nah, that was not going to work. Okay. All right. Just trying to get my pen back. There we go. Excuse me just a moment. I'm so sorry. I think I told you earlier, I'm pretty sure I did, that I had a pretty rough weekend when it came to, I don't know what has happened to Jemanuel, and I don't know what's happened to the rest of them. I'm wondering if they're all having trouble getting in. Jemanuel's the only one I've seen. Okay. Let's put the three here and the 1 there. Okay. Let's see if that works. 2m times m is 2m squared minus 6m plus m, that would be minus 5m minus 3. That certainly works. So here we have m is equal to minus 1/2, and here we have m is equal to 3. I hope that wasn't too fast of doing that, but that's what you have. Well, what's your solution then? Y is equal to C1 e to the minus x over 2. That's from the m equal minus 1/2 plus C2 e to the 3x. Okay. Now that's our solution. We weren't given initial values, so we can't figure out what the C1 and C2 is, but that's your general solution. Let's see how they did. Y is equal to C1 e to the minus x over 2 plus C2 e to the 3x. Got it. Okay. So there's your first case. Well, yeah, 2 distinct real roots, first case. Now, just because I've taken so much room to write, I'm going to change it to, clear this. Do you need to see that any longer? You okay? Okay. Here's the second case. I'm going to bring my book over so I can read better. Y double prime minus 10y prime plus 25y is equal to 0. Okay, a linear second order differential equations with constant coefficients. Okay? Now we could start again and say let y is equal to e to the mx. Then go through all the work there and you still come up with the same, well, an auxiliary equation that looks like this. M squared minus 10m plus 25 is equal to 0. Now, do you want me to show you why that comes up again, or are you okay with it? That's your auxiliary equation. Notice the second derivative becomes a second power for m. First derivative becomes a first power for m. The zeroth derivative becomes a zeroth power for your m, which is 1. And that's equal to 0. That's your auxiliary equation. Now, if we were to try to factor that, it would factor as m times m. It's the only way you'll get an m squared out of it. And then you happen to notice this sign is positive, that's negative, so both of these have to be negative. And what two numbers multiply to be 25 but add to be 10? 5 and 5. Now, one thing you're down to here, now I don't know what that is there. Let me see if I can erase it. Okay, m minus 5 times m minus 5. I don't know where that other mark came from. I can't get my drawing pen to come back. Okay, that's what you got. Well, that's obviously m equal 5, but it's a double root. Okay, what can you do with that? Well, what we said before, using what we did in the earlier section, I think it was 4.2, this gives you 1, y is equal to c1 e to the minus e1 e to the 5m. Whew, my brain is going on me. Now, if you wrote down c2 e to the 5m, you could add those together and just make the c1 plus c2 a new constant. Doesn't get you anywhere. But because these two are identical, then what we do here, and by the way, it's not m. I don't know where my brain is today. I'm having a lot of difficulty. The variable here is x, not m. M is equal to 5. So that e to the m 5x. And the second one would be c2 x e to the 5x. That's what your repeated roots give you. Okay? And there, sure enough, is the solution. And you'll see that in the book. There, y is equal to c1 e to the 5x plus c2 e to the 5x. X e to the 5x. Sorry, I'm reading it, can't even say it right. All right, excuse me another minute. I need some sort of liquid. Goodness gracious. Okay. Let's do the third example, third part of example 1. And this one, I'm almost certain we will need more of the screen. Okay. Let me get the book back in my lap. I tell you, I have all weekend I've been running out of energy so fast, it's unbelievable. Here's our y double prime plus 4y prime plus 7y is equal to 0. Okay. Now, This is a bit more involved, and I think I want to go on and go back to the basics on this one. Well, I think we can do it. Let's go straight to the auxiliary equation. That would be m squared plus 4m plus 7 is equal to 0. If you went to the original, and I always still like to write it down. Yuck. Let y equal e to the mx. Okay, that's where the m's come from. So I still like that. Try to factor this till the cows come home. You'll never get it to factor. Okay, 7's a prime number. There's not any two numbers that 7 factors into that add to be 4. It just doesn't happen. So what we do for this one is the quadratic formula. M is equal to minus b minus 4 plus or minus the square root of 4 squared, which is 16, minus 4ac. Here's Ryan. Good deal. Okay, while Ryan's coming in, let me mark him present. Jemanuel was here for a few microseconds and he never could stay in the class. Ryan, you haven't been in touch with Jemanuel, have you? Okay. Do you have a way to contact him? I send him a chat, but I never got whether he got it or not. Okay, see if you can. Tell him I kept trying to get him in the class and he kept popping back out again. And finally he quit. So I don't know what was going on. His internet, Zoom, I don't know what it was. But anyway, tell him we're still here. Okay, that we did try to let him in. All right, what we're doing here is a differential equation, a linear second order differential equation with constant coefficients. And always with that kind, the assumption is let y equal e to the mx. And when you plug that in, its first derivative and second derivative, you wind up with an auxiliary equation, which is not a differential equation, it's a quadratic equation, or more generally a polynomial equation that's equal to 0. Okay? And because this is not factorable, we're using the quadratic formula on it. That would be minus b plus or minus the square root of b squared, that would be 16, minus 4ac, 4 times a times c. Now I wrote out the ac here, I didn't in the earlier, all over 2a. Well, that a is 1. Well, the a here is 1, okay? And the c here is 7. Okay, I know that's ugly, but I think I will erase it to make it a little prettier. Okay. Okay, 4 times 1 times 7. Okay, that's AC over 2 times 1, A. All right, now what does that give us? Minus 4 plus or minus the square root of 16 minus 28. 16 minus 28. Now usually when I do this, the first thing I do is count the number of minus signs. The 4 is always a minus sign, but the A here was 1, the C here was 7. So only one minus sign, that makes that negative, over 2. Okay, 2 times 1 is 2. What does that give us? Minus 4 plus or minus the square root of negative 12 divided by 2. What does that give us? Minus 4 plus or minus the square root of -1 times the square root of 4 times the square root of 3. -1, pull that out, then you got 4 times 3 left. This is all over 2, and that gives us -4 plus or minus 2 root 3 times I over 2. Well, this 2 will go into that 2 once and to this 2 -2 times. So here's what your solution is. M is equal to -2 plus or minus the square root of root 3. Oops, I put 2 square roots there. Jemanuel or James? Okay, yeah, it was Jemanuel who was trying to get in. I didn't know what happened to James. I hadn't seen him yet. That's okay. I didn't mean to bother him or anything. It was Jemanuel. I just wanted to let him know I wasn't ignoring him. I just couldn't get him to stay in the class. Okay, sorry about that. Okay, now -2 plus or minus the square root of 3 times I. Okay, I usually like to write I root 3, and this, and it's not over anything. Okay, now if you go back to case 3, and let's just do it, I'm going to erase. Excuse me. I'm so sorry. Okay, I'm going to erase this and erase a little bit of that. Okay, try to make it a little neater looking. Now let's go back to our, well, my pen, oh, there it goes. It sometimes shows up and sometimes doesn't. Let's go back to the book for a moment here to remind ourselves what the answer is going to be. Okay. And I'm going to have to move you just temporarily. I don't know what happened there, but anyway. Okay. Here's the bottom line. When you have a form that's like this, you have y is equal to c1 e to the alpha x, alpha is a real number, times cosine beta x plus c2 e to the alpha x times sine beta x. Both alpha and beta are real numbers. And you can factor out the e to the alpha x, and yeah, okay, let me just make sure there's nobody else trying to come in. No. Okay. Factor out the e to the alpha x, and you get a c1 cosine beta x plus c2 sine beta x, where this e, this is such a pain in the neck for that to roll up like that. Okay, that's what you come down to. Now in our case, the alpha is the, I believe it was 2, and the beta is the square root of 3. Okay, if you recall back from that, let's just go back to that. Yeah. Well, I thought it was going to show up better than this. It seems like when it jumps the page here, it just leaves you hanging. Okay. But the alpha is the real part, beta was the imaginary part, So let's go back to where we were, and hopefully you'll see this on the whiteboard. See, here's the real part. That's your alpha. This is your beta. Okay? So we write this as y is equal to e to the minus 2x, that's the alpha here, times c1 cosine beta x, that beta is the square root of 3, plus c2 times the sine of the square root of 3x. Okay, that's our answer. The real part goes here, the minus 2 goes here as the coefficient for x, and the beta is the coefficient for your imaginary part, so that's cosine root 3x plus sine root 3x. You put a arbitrary coefficient with each one, and that's what you see they give you in the book. E to the minus 2x times c1 cosine root 3x plus c2 sine root 3x. Remember, the root 3, whatever this is, that's what's under. The x is outside the radical. That's why I'd sort of bring down the housetop there to make sure you don't try to stick that back in. All right, so there was example example 1. Okay, now let's do what we just did. Okay, now I'm going to move Kara again, sorry. Okay, and let's go to example 2, which happens to be an initial value problem. And for some reason my whiteboard is moved up a little bit too much. Okay. Okay, I think that's better. Here's example 2. Solve this. For y double prime plus 4y prime plus 17y my pen's not writing well is equal to 0. Given that y of 0 is equal to minus 1 and y prime, oops, just one y, that's ugly, plus, and y prime at 0, remember initial value problems have to all be at the same place, is equal to 2. But they don't have to have the same values, obviously. All right. Now, sorry, I've got a frog in my throat. For those who've just gotten here, we were burning a lot of brush this weekend, and my head is just all clogged up. Okay. Now, just like we did before, take the differential equation here and write the auxiliary form. Now, since Ryan came in recently, let me write down what the assumption is. Y is equal to e to the mx. That's anytime you have a linear second order, or actually higher order, differential equation with constant coefficients. As long as those are real numbers, no variables in them, then this is your assumption. And if you were to take the first and second derivatives of this, you'd find out that every derivative adds another m to it, so you come up with what they call the auxiliary equation of 4m squared plus 4m plus 17 is equal to 0, because your e to the mx's factors out because it's never equal to 0. So you're left with this. Now, that one, try to factor it till the cows come home. You'll never do it. So we'll go straight to the quadratic formula, which tells you that m is equal to minus b minus 4 plus or minus the square root of b squared, which again is 16, minus 4ac. Okay, there's only one minus sign in that, so it's going to be minus 4 times 17. That's 28. I think it's 68. Okay, and this is divided by 2 times 4. Okay, now I'm so sorry, I'm drifting badly. Goodness. This is minus 4 plus or minus the square root of well, 16 from 68 would be 52 plus or minus, or that would be a minus 52, all divided by 8. I should have left the 4 in there, but it'll come out. Minus 4 plus or minus, now 52 just happens to be, well, minus is minus 1. Okay, 52 is 4 times 13. Factored out the 4 because it's a perfect square. And then this will be, I'll leave it 8. Okay. Now what will that be? That's a minus 4 plus or minus, this is your I, that's a 2i, and this would be 2i onto root 13 divided by 4. Well, 2 will go into 4 twice, 2 will go into negative 4, negative 2, and 2 will go into 2 once. Alright, so what do we have? Your first m is a minus 1 plus or minus I onto the square root of 13 over 2. Okay, now that's sort of an awkward way to write it, but that's okay. So what does that give you for your solutions? Okay, y is equal to, well, here's the alpha part, that's e to the minus x, okay, times your c1 cosine of the imaginary part, the square root of 13 halves times x plus c2 times the sine of the square root of 13 x. Okay. Why did I put it down? 13 halves x. Goodness gracious. Now, what we're going to do is plug in our initial conditions. Okay, y when x is equal to 0 would equal to e to the minus 0 is 1. Okay, so that's not going to contribute anything. c1 times the cosine of 0, which is 1. Okay, so that's not going to contribute anything. Plus c2 times the sine of 0, well, sine of 0 is 0, so that's not going to contribute anything. So c1 has to then be minus 1. Okay? C1 is equal to minus 1. Now let's take the first derivative, y prime. Well, this is y. So y prime is going to be, now here unfortunately it's a product rule, but it's not too bad. The first, which is e to the minus x times derivative of the second, which is c1, but we know that c1 is a minus 1, so let's just write that as a minus 1 there. Cosine square root of 13 halves x plus c2. We don't know what that one is. This, okay, I'm taking derivative, I forgot to do that. Derivative of cosine is minus sine. Okay? Okay? And you have the chain rule of a root 3 over 2. Square root of 13 over 2. This is really getting ugly, isn't it? Plus, okay, c2 times the cosine, taking the derivative of the square root of 13 over 2x times, and you got to get the square root of 13 over 2 here for the chain rule. Okay, now let's set that. Okay, that's your y prime. So y prime at 0. Okay, that's a y prime. I don't know why it did an extra little thing there. Okay, that's equal to 2. Okay, so let's plug in a 0 there. Oh, I'm sorry, I forgot to do the second half of the product rule. Okay, plus the derivative of the first, which will now be minus e to the minus x times the second, which is c1. Well, we already know that to be a minus 1. Cosine the square root of 13 halves x plus c2 times the sine of square root of 13 x, 13 halves x. Okay, it's hard to read. Goodness gracious. Okay, now we've got to plug in 0 for x. Okay, well, 0 for this x gives you a 1. Okay, 0 for the x here, the sign of 0 is 0. 0 for the x here gives you a 1 here. So we have, and this is equal to 2. I just don't have enough room to write. Let me see if I can erase some stuff here. There we go. Okay, I don't think I need this anymore. Nor do I need this anymore. I hope I don't. If I do, y'all have to recreate it. Okay, sorry about that. Okay. All right. So what we have then is y prime at 0 is equal to 2. Okay, and that's equal to, and this, okay, this is the one down here. This will be e to the 0 is 1 times the square root of 13 halves times 0, so that's going to be 0, plus c2, okay, Cosine of 0 is 1. So this is going to be the square root of 13 halves minus, and here again e to the 0 is 1, and that's a minus 1 there times 1, so that's, I think that's a minus 1. I think that's all that's left there, and this would contribute 0 because sine of 0 is 0. Alright, so this then, I think, if I have done it right, and there's no guarantee of this, let's add 1 to both sides. You get 3 is equal to C2 times the square root of 13 halves, and that would mean that C2 is equal to 6 over root 13. This is a weird looking answer, so I'm not sure I've got it right. So that would give you y is equal to e to the minus x, this pen is not working well, times, now the C1 was simply minus 1 cosine root 13 over 2x plus 6 over root 13. This is the part that doesn't seem to be making a lot of sense, times the sine of square root of 13 halves x. Okay, let's see how badly I botched it up. Okay, I did. I don't really. Okay, sorry about this, folks. My old gray cells are not thinking very well today. Okay, first thing, we should have had a 1/2. I think I lost my denominator, but I don't. Yes, I did, because that, no. Okay. I really botched it up. Okay, let's go back to our original form. We had the auxiliary equation right, so I'm going to go back and just do a lot of erasing here. Okay, let me erase this. I think I've already erased some of what I need, but I should have been paying more attention to the book. Okay, I think I'll erase most of what I got because something is dreadfully wrong. Maybe I should have just cleared the screen. It would have been easier just to write everything back again. Sorry about this, folks. Okay, let's see if I can clean this up in 10 minutes. Okay. All right. All right. Let's start this over. M squared, or 4m squared plus 4m plus 17 is equal to 0. That's our auxiliary equation. Okay, quadratic formula gives us that m is equal to minus 4 plus or minus the square root of b squared, which is 16, minus 4 times, that's where I did it. I didn't put this 4 in there. I did one 4 but not the other 4. it's a 16 times 17. I'm going to pull on my calculator to tell me that one. Okay. Okay. 16 times 17. 272, quite a different number. Minus 272, all divided by 2a, which is 8. Sorry about this. Okay, so it's 272. I'm going to subtract 16 from that. That gives me 256. So that gives me a minus 4 plus or minus the square root of a negative 256 divided by 8. Okay, now I know beyond the shadow of a doubt that there is a 16 in that. Okay, so 256, I'm going to take a square root of that and see what I get. I don't think I'll get a whole number, but let's see if I do. Square root of that is 16. It is a perfect square. Okay, so that'll be plus or minus 16i over 8, which will be minus 1/2 plus or minus 2i. All right, the real part here, the alpha is minus 1/2 and the beta is 2. Okay, so this is much, much better than what we had before. Y is equal to e to the minus x over 2, there's your alpha part, times c1 cosine, the beta part is 2, x plus c2 sine x. Okay, now we can plug in our initial condition. Y of 0 is equal to, this still comes up to be a 1. Okay, this comes up to be a c1, and cosine of 0 is 1, plus sine of 0 is 0, so this is equal to minus 1. c1 is minus 1. Y prime of 0 we're going to do next, but we need to know what y prime is. So let's go back to our okay, let's just do it of x to begin with. Let's just do y prime. Okay, yeah, it's of x. Okay, let's do that, and you have the first times derivative of the second, e to the minus x over 2 times 2c1 minus 2c1 sine of 2x plus c2, this is a 2 here I left off, 2c2 cosine 2x. Okay, that's the first times the derivative of the second plus the second times the derivative of the first. The second is just c1 cosine 2x plus c2 sine 2x times the derivative of that would be minus 1/2 e to the minus x over 2. All right, This is messy, but doable, I think. I'm hoping it will be anyway. Okay, let's plug in what we know. Let's make this y prime at 0, and we know that's equal to 2. That's going to give you a 1 times, and this was a -1 times a -2, that's going to be a +2 times the sine of 0, that's not going to give you anything, okay, times C2 times the 1, okay, plus C1 was a -1, cosine of 0 is 1, okay, plus C2, which is 0, I mean sine of 2x is 0, and all that is times a -1/2 of 0. Okay, so what do we have here? 2 is equal to C2 minus, no, plus, because there's a minus, there's a minus, 1/2. I think that's it. Okay, so C2 is equal to 3/2. Did I get it right this time? I don't think so. Okay, sorry about that. What is C2 equal to? They get 3/4. Have I just made a dumb mistake, or is it worse than that? We are almost out of time. We get 2 C2, I got 2 C2, and I must have, seems like I had a 2 there and wiped it out. Yeah, this was supposed to have been a 2 there. I had a 2 in there, and then I wiped out a 2. I don't know why I did that, but that should have been 2 C2 here. Okay, plus 1/2, and that would have then been C2 is equal to 3, or 2 C2 is equal to 3/4, so C2 is equal to 3. 2 C2 is equal to 3/2, C2 is equal to 3/4. I don't know why I got that wrong. So then you plug that back in here, and you get y is equal to minus, or e to the minus x over 2 times -1 cosine 2x plus 3/4 sine 2x. Okay, no plus c's required because you had a definite thing. Okay, they show the graph of that. I can't see where my camera is, but somewhere there you can see that in your text, and that gives you that. I'm sorry, the old gray cells have just decided to go to sleep this afternoon. All right, we will pick up there with 2 equations worth knowing. Okay, all of these equations are worth knowing, but 2 that really stand out that you see a lot. We'll begin that on page 137. Homework exercises here for this one. This is a sort of a long section. Any of the odds 1 through 13, they should all be in the back of the book. Any of the odds 15 to 27, they should be in the back of the book. Any of the odds 29 through 35, they should be in the back of the book. Either 37 or 39 should be in the back of the book. Oh, wait, let me not go too far. Let me back off. Just do 1 through 13. Any of the odds 1 through 13, because those are all second order differential equations. We haven't gotten into the higher order. We'll get there, and it'll be a pretty straight transition, but it won't be. Let's not do it now. Okay? Any questions? Sorry, today turned out to be pretty worthless, but I usually like this section. But boy, I guess it's the anemia and just overall tiredness. All right, any questions? Okay, I'll stop recording now. Remember, we do not have class on Wednesday because it's Veterans Day, and we will meet again next Monday. Now, Kara, we'll see you tomorrow, and Ryan, see you next Monday. Good deal. Any questions? Okay. Okay. I'm a bit behind on emails, and I've got to get ready for tomorrow's classes, but once I get that done, I hope to be able to hit some emails this evening. Okay? All right. Good deal. Yes. Uh-huh.